perfect. Wow.
Everything works.
Exactly. So good morning, everybody. First talk this morning is by Reverend Lin about lattice-QCD Parton distributions, progress, and what we can do. Thank you. And we have also the clicker.
Yeah,
and actually an automatic one I saw.
Ah, that would be great. Yes. Sorry. I should.
All right.
Cool. Thank you.
There you go.
Thank you.
Thank you for the invitation. So nice to be here. So I'm going to tell you a little bit about what lattice-QCD have been doing in terms of the Parton distribution functions. And so, anyway, so there are obviously this audience doesn't really require this full description of that, but there's exciting about EIC, and one of the motivation that getting into this business is try to really look into the SQL to see what we can do on the lattice-QCD side. And so just a quick word about, you'll have more details from the global analysis, but just for general descriptions. So we have a lot of data that we can use to try to get PDF, and it's not exactly easy test. You know, with all the experiments very different, so you actually require very different theory inputs. And so different combinations or experiment combining how you treat, for example, the charm, or how you treat the strange assumption you made, you get slightly different PDF. So there are multiple set of PDF, and at the end of the day, people try to compare them to see whether they all check out. And so there are more than, there are more than one set of PDF for the polarized case, and a little bit less for the longitudinal polarized, and even less for the transverse ones. And so one of the things that I motivate us to do this lattice calculation is there's always at least a few years ago when we started, there's a big discussion about how you parameterize the distribution functions. So the most common ones people use x to a certain power 1 minus, and then there's px vary from different collaborations. And so you can do, in early day, they do a simple polynomial. Now they have more a fancy way to expand it, but there's always some discussion of how many parameters you need. Because more parameters you put in here, you get something really big with a big PDF, and then nobody wants to use them. And if you use less parameter, you get very precise, but then start to worry about, are they always systematic? That you don't know a lot, you might just coincidentally be right, and so on. So one of the motivation we hope eventually lattice-QCD will be able to people will be able to check this parameterization. We don't want to assume them, so that's one of the motivations. And another issue is things like the common assumption in terms of, say, the strange, because you don't have the very good data to constrain them from the PDF analysis. So very commonly, people have been assuming strange equal to the anti-strange distribution. And it picked the data because they have not much precise data to constrain anything, and sometimes people even constrain them with some combination upon the equal with some anyway. So, but again, the data doesn't. You don't have that information, so a lot of assumption actually fit the data, right? So at the end of the day, hopefully, eventually, we will be able to provide some help to remove some of the assumption that people use, or provide certain cross checks. So there are two. I think that eventually will be something hopefully we can do with the lattice-QCD. And so this has been shown. I've been just taking one of the summary plot from the CJ15. They are probably more latest ones. So here we just compare a ratio. For example, if you look at unpolarized distribution, there are many global fit. This is the most well-known PDF. And even so, if you look at the D-quark distribution, divided out by the central value of them. And so the key point is very different collaboration. Even though they try, there's a still big uncertainty in the large S regions. And obviously the EIC is going to tell us on the small S region that we can constrain. And the other quantity, things like strange, for example, that I mentioned, because not much good data to constrain. So, there's a large uncertainty over there, and then large uncertainty in the gluon case, and also the anti-quantum distribution that's not much constraint going on there. So these are all the area. Hopefully one day we will be able to use lattice-QCD to help to constrain some of these distributions. And so what can we do on the lattice? I'm just going to skip the lattice-QCD introduction. I'm sure yesterday you had a lot of good introduction to that. So for this talk, we're currently working on the leading tricks, mainly the polarized PDF. We look at the helicity, computer polarized, and transversity. So they are all simpler functions, but even so, as you go down to the transversity, you get very little data. And in the past, lattice-QCD have been calculate something called moments, which is the integral of the individual distribution function. So in principle, the idea, if one can have enough moments, we'll be able to do the inverse problem and extract the individual distribution function. And the issue is, on the lattice, we call it the symmetry. And so going down to the higher moments are actually more complicated. And so you have a lot of operator missing issue you have to worry about. It's kind of a nightmare. And the errors actually in the past. So here's one of the past study trying to go beyond the leading moments that people currently most commonly calculated. I just wanted to point out the date. This is all more than a decade ago, just to show you how complicated they are. And the SS function here is the pi mass squared. The physical pi mass is over here. So this is all super heavy pi masses, larger than 800 MeV in today's standards. They are really heavy. And they are all, there are some mostly quant and some two flavor, very simple calculation. But even so people haven't really attempted to calculate them yet, just because there's a huge complexity involved. You know, literally had to devote a PhD student to do nothing but figure out the operators along and stuff like that. It's very complicated, and it depends on the fermion actually we use. So it's not, at least how the work has been done before. So there are ideas trying to go beyond the moments, and so this is some like a holy grail for many people who do the structure calculations, because that is not just a PDF, they are GPDs, TMDs, distribution functions, and maybe one day we can think about binary distributions. So there have been a lot of ideas, so I don't want to go do all that. I just want to point out you should pay attention to a lot of exciting development that's going on. There are a few ideas trying to go beyond the higher moments, and they are actually making really good progress with this idea. So you might see a few more papers coming out there. And another direction is to try to calculate the direct X dependence. So you heard about the Johnny tensor yesterday. There is also a Regensburg method. Sorry, this is QCD-SF. They have been called different names so far, but there's also another direction there. There's an Euclidean correlation function. It's probably called position correlation function. It's not here. It's a Regensburg and group. There's a lattice cross-section method that's proposed by Junwei and the other people are working on that. And then there's also an idea about the large momentum effect theory, and I would just call this a general classification. They are very different how you carry them. For this talk, I'm going to focus on the original Lamont method, and some people call it quasi-PDF. And so these are the collaborator I'm going to present the work on. And so I highlight a few of the younger people, and actually Yibo Yang is now a faculty in China, so it's need to update this. But there are, I just want to point out the young people, Zhao Yong, Yushen Liu, who used to be a grad student here, and Zhenhui Zhang. They have been doing quite significant contribution to our work. So a very brief slide about Lamont. So you have heard this talk, probably have heard this method a few times here now. So the idea is to try to calculate the Parton distribution function and take the infinite momentum frame as originally Feynman suggested. So what is proposed is on the lattice we can calculate some kind of intermediate quantity, and some people call it quasi distribution functions. And what we calculate is you can, for example, this is an example from the unpolarized case. You can have different gamma matrices corresponding to different gamma structure. We have this, instead of Lycon link, we have the gauge link. You put in the moment, the nucleon as specific momentum. And then at the end of the day, you calculate all this on the lattice, do a Fourier transformation, and you can get this quasi-distribution function. it's not a true Lycon distribution function. It does have a momentum dependence. So you have to take this proper limit. And so the idea would be when you go to large momentum, you want to take you'll be able to recover the Lycon functions. And so this is very similar to some limit we have been taking in the lattice calculation. For example, we never take measure any quantity with a equal to 0, but you take like fine enough base spacing, and you can remove that assumption. Also, similarly with the volume, right? If your volume is big enough, your measurement doesn't depend on your volume anymore, and that's where it can become useful. Obviously, taking this limit is not trivial business, so there's a lot of Gaussian going in, and that's why I have our collaboration. It's composed with perspective QCD collaborator to properly taking those limits. And there have been a lot of development going on here. I just steal a slide from Zhao Yong, who did a plenary talk in CPAC earlier this summer. And so if you are interested to find out what has been done about various different issues up to then, we can go in and look at the slide later and figure out what they are. For this talk, I'm just going to concentrate a little bit about what we do on the lattice side. And so to do this calculation, firstly, like everybody else, we need to take a lattice. So we are doing something called sliding. We take a 2 + 1 + 1, which is up-down, strange, and charm, 4 flavor QCD vacuums. And then on top of that, we use a different fermion called Clover. And so that will make our calculation a little bit easier. And so what we do, we create a nucleon with a specific positive momentum. For easy choice, I just put the momentum in the z direction, and analyze it in another space-time. And so instead of, so we try to send in a plot. This plot is not a point plot. It's more like you are plotting them as a distance in the space direction. And this makes the lattice-QCD calculation easier because we can do this displacement easier in terms of numerical. And so at the end of the day, you got a bunch of matrix elements. It's a function of that displacement you have and the momentum you're boosting in the nucleon mass. And so then you will have this is not going to be a real matrix element anymore. It's a complex number. So you can actually take a specific momentum. For example, this is one of the examples we use on our physical parallel mass calculations. And so there will be as a function of the z. And here we have 4 different data points and the different way to try to analyze this matrix element to make sure they are consistent without, there's one thing called steady state contamination. We are trying to make sure that it's under control, and the point all agree with each other suggests that we had that under control. And my new postdoc, Rachel Lee, actually coming from a different collaboration before, and she actually take our binding data and try to do even a higher state, including even you can think about it as a more higher leading order, next leading order term into our state, and they are quite consistent. Anyway, so this is one of those things you have to do on the lattice to make sure that your matrix element we can trust them, and then you move forward with them. And then once you have that, then in principle you want to renormalize those matrix elements, and that probably by itself will be another talk. I'm not going to go too much detail into that. So you take them original variance element, you try to normalize them on the lattice scheme, and then you can reconstruct something called quasi-PDF distribution function or quasi-PDF. And so this is what it looks like. It doesn't, so this is the same 2.6 GeV nucleon opposite momentum calculation we had, you see earlier. And so it doesn't have to, in the past, when we use smaller momentum, it can actually go beyond, there can be distribution beyond the larger than x1. In this case, it wasn't. And here, just a pure Fourier transformation from this what we call iron scheme minimization, and it depends on the scale we choose and how we set the minimization. And at the end of the day, we want to remove that and then translate them whatever scheme we choose on the lattice-QCD, and convert that into MS bar that we can compare with, and also remove the momentum dependence. So they're having a number of work lately to do the specific thing we need. There's INT-18-3 and Yongzhao. They first figured out for how to do that for unpolarized, and our operator, we later extended it to the operator we use that doesn't have missing problems, and the transversity operator that also been worked out by Michelle and Theo, Igor, and Yong. And then there's this mass correction term. It's a little bit like a target mass term that we have worked it out before, and we have been find in this momentum we use, the correction is actually quite small compared with our statistical terms. And there's also this potential higher twisting term that can come in. And we have been always trying to, we work out the operator in this paper. They also been worked out with other data people before. And they are really complicated. So right now we don't propose to directly calculate them. They are within the within the error from our current statistical error. And we currently, in the past, we tried to extrapolate away. But right now we have been seeing they are quite small, and we don't see a difference, much differences. And the whole framework is very similar to what people do in terms of having quantitative theory. There you try to explain the operator in terms of dependence on the masses, and then you try to control them systematically as much as you can. So there is so the final thing we do is this thing called matching. So this is the quasi PDF we calculate on the lattice, and the blue one is the true Lycombe distribution you need. And after you remove all that, and that's this green, the blue distribution over here. So this is differences between up quad and down quad that we call isobector combination as a function of positive x, and the negative has here corresponding to the anti-quad distribution functions. And this is actually quite important in terms of how to shut out our final distribution. The contribution is still quite sizable. And there are a lot of people talking about quasi-PDF, but they didn't apply this final matching in their preferred QCD model, and they're actually quite different. They are actually quite different objects in terms of quasi-PDF and the PDF.
So,
Well, you don't repeat the Why don't you answer the question?
Well, my question is my question is very stupid. So is it obvious that PZ comes in only as powers?
Yes.
Why is it obvious?
Huh?
Is it obvious that PZ comes in only as powers? Do you get logs of PZ?
I think you can. I think you can, but with some powers of suppression, I can't remember what it is now.
So the leading term Z has no logs of PZ.
I need to look into that.
My question is really, so what is the meaning of the uncertainty bands in these papers?
So right now it's just statistical errors.
Okay, I see. So the message is also that there's matching is a large effect compared to those statistical errors at this point.
Right. So right now we take this step, assuming because we only have one lattice spacing equation, we can assume that this is assuming there is a very small lattice spacing dependence, boundary dependence, and so on. So that's a tiny assumption that's been made there. But in principle, you want to take the proper continuum limit before you apply this final step.
Yeah. But it's not just outwards and upwards, or it's going to be hypothetical or okay. Because compared to I think that has to be different. And to compare PDS from the terminology, it has to be perfect. Because that's the apples to apples.
Right.
But the green could be different.
Right. Anyway, I have a plot.
Sure.
I have a plot.
That is true, but you don't know what the truth is.
Yeah,
So,
at the end of the day, it's of course a
because-
physical object, right?
exactly, because a PDF is a PDF, and normally we extract it through fits. And now I have a match PDF, and this matching function is not obviously changes enormously the shape. So how do I know that it is the right matching function? Or what the uncertainty of this matching function is?
The matching function is calculated.
Yeah, to one loop.
Yeah, I think they calculate higher loops.
In principle, you can calculate higher loop, but that's
So I guess
Really
this is where my question comes in. If you look at logs of PZ, and you want to take a large PZ limit, you have to reassemble those logs. If you have logarithms of PZ and you want to take a large PZ limit, you need to have control of all those logarithms. You have to calculate all of them, don't you?
yes, I did. So the differences between these two is mainly the ultraviolet contributions. I don't think there's so one here. There's so most of the one are coming with a higher twist. That's the part I'm not quite sure about whether they are low.
That was the name of the game. The people have been doing exactly that, right? Resumming the large logs. Oh no. No?
Here?
I don't think so.
Yeah. Yeah.
They are so hard. They are the same. So we don't have to worry about it.
Not even a one loop calculation.
It's just
One loop.
but there's no logs of one loop.
There is one loop.
There's one loop.
And one loop.
So the two loops and the two logs.
Yeah, exactly.
I'm just saying that there might be BFK tied in there because you're really just taking the high energy limit. And that's what it does. You know, your log of PZ is proportional to log of the center of mass energy. Logarithm of PZ is proportional to the logarithm of the center of mass energy. And maybe, I understand you have a separate X variable, so, but it might be somehow related to BFK summation. And then, you know, then you back to the old problem.
I mean, we have to deal whatever you continue problem you have eventually. Yes. So this matching is done continuously. So, and we do have additional issue to worry about. So it's more complicated than the continuum part of the calculation. But you can take the continuum limit and large PZ to infinity will be covered whatever you have in the evolutions and disease.
You're not claiming that this is the complete thing. This is just one loop, and we do know, we do expect that tool contribution, especially if the momentum is not large enough. This is sizable.
No, but it's not just sizable, it's dominant, right?
The dominant compared to the one loop.
Yeah. If you have
But-
expansion in a log of PZ and PZ goes to infinity, the higher powers of the log of PZ
But it's
will always
suppressed by
be
a
a
power
number.
of g to the fourth. So you have
Yeah,
the
yeah, but your PZ is infinite, right? No matter how small, and your G is fixed at the scale mu, I presume. So G, when you take a PZ to infinity, your coupling is fixed, your log of PZ is increasing. So why don't you guys worry about this?
So we want, so that probably in a year from now, we will have the two location.
So
There are people looking into this, and
Yeah.
so probably from a year from now, we will have the expression. And
Isn't it also an X-dependent question? I mean, if I draw this thing to the phenomenology, right? Of course, higher order corrections will matter, but it will matter in different regions of the
Right.
kinematics.
Right. So the
If
PZ coupled with the
I'm in a very small X region, yes, I have to do estimation.
And
I'm
a
not
small
talking
S
about
does
lots of
have-
S, I'm talking about lots of PZ. And the technical limit before you compare with any data, right? You have to take PZ to infinity to understand this procedure. If you have lots of PZ and you take PZ to infinity, you better have full control over them before you compare anything to this. So
My question was about, so you said, you write separately that the power corrections, that you specify the one dependent on the mass and the, is that like the kinematical target mass correction? The first one?
this one?
Yeah,
Yes,
I
that's
think so. Yeah.
it's kinematical.
Yes.
So in principle, has that been taken care of or?
Yes. In our case, we evolved into when we call match, we take it into this term. This is slightly gray.
I have this, yeah.
Yeah.
Okay.
but they are tiny actually in the momentum we're looking at. So no other really sizable. Anyway, so I just want to point out that we have come a long way. So we have the first calculation in 2014. I don't want to get into too much detail because of the time. And so we are calculating the, obviously one of the issues we want to address is the C-flavor asymmetries. Then we also have the first helicity and transversity calculations. And just updates on so in the recent years, we have been us and ETMC, we both have a different way of doing the non-predictive realizations. And there are more than one group that's doing slightly different way of try to deal with realizations. And we also, there are some issue with the truncation effect in the Fourier transformation that we also been trying to work out. So there have been two very exciting physical plan mass results, both are single lattice spacing, but these are very specific calculations. And so our earlier result last summer and the earlier ETNC result, again, we only look at the isometric combinations, and the roughly the momentum, roughly largest momentum we use still small. So you can see actually quite a bit of discrepancy, and especially when we were looking at our comparison, we see the C-quads actually quite sensitive to the momentum distributions. They can actually kind of change in sign there, but this is the statistics we're working on. And similarly, you can also see some of the comparison between ETNC and some of the homological fit. That's still quite in the C-quad region, still quite hard to reach. And this is when we are now. So you see some of the funny distribution here, because both our collaboration are not using any of the permutation forms that we commonly use in the global PDF. And you see a lot of pretty distribution from lattice-QCD. If you assume this form, you suppress automatically the large X distribution, so you won't see this kind of distribution function. So this is just one way of trying to understand. Then first is control our calculations. And secondly, is really try to see when you don't impose this assumption, what kind of distribution you get.
Now I'm getting confused, I must admit.
Yeah.
Because I just learned yesterday that lattice is an ab initio calculation. If I do an ab initio calculation, I would not need a parameterization for my PDF.
And we do not use it here. But there are other groups.
Yeah, but PDF, for example, does it. They are using a Monte Carlo method, and so actually the error bars, that's why the error bars are, and so they don't, larger, exactly. So they don't have this parameterization bias, and most of the groups have actually evaluated their parameterization bias. Now the question is, your uncertainties, which you show here, are again only statistical, or what are they?
In these two cases, they are only statistical.
Which of course is not a very fair comparison. Right. Yeah, but I want to. Yeah, no, wait. I want to make this point because there is a lot of. If I go to conferences lately, I hear, "Oh, why do you need to measure everything? Everything can be calculated on the lattice." I have heard this lately 5 times as I have been on the conference. And showing these comparisons where NMPDF goes through, I don't know how many groups, for example, calculating their uncertainties. Comparing that with a statistical uncertainty is not exactly fair, and not even saying it on the slide.
Right. Okay. So first of all, we are not doing a quantitative comparison here. We use them to see how.
Are not experts and see these plots don't know this.
Okay. So I think in the paper we specify them, what we are comparing with, and so later our updated work, which is here, we try to estimate what we can with systematic. So this is the latest one we've done. We changed the momentum to 3GED. And we have actually tried to estimate the uncertainties as much as we can anyway with this simple one lattice spacing calculations. And we just compare with one. Again, this is kind of just to guide the eye to see how things work. We are not trying to, anyway.
Regarding this point about NMPDS, we go back to previous slide, you know, despite the fact that everyone and they claim that they are using a completely parameterization independent object, they do have X to the alpha 1 and X to the beta as a
Right.
Not
That might
a P.
come out.
Yeah.
That might come out as a result of, yes.
So what I'm saying is that it's not entirely true that they will never be able to get rid of that, because that is essentially needed always in any phenomenology. I mean, if you don't have that, then their analysis is kind of very difficult to figure out. So it's not entirely fair to say that NPDF is the only group who can get rid of that exponent.
I have not said that. I said they do a very big effort in calculating their systematics.
The thing
And
is,
they do.
we
Yeah,
discussed-
also, that's fair, that's fair.
So I have not, so, and there are uncertainties, and you see that, for example, for the low XX populations and so on, most of the other groups have kind of well behaved, and as soon as there's no data, their uncertainties explode, and that is also true at the high X.
Sure.
So,
There are also theory, sorry.
Sorry.
There are also actually theory uncertainty that most they haven't quantified yet, so they do make an assumption. I think they still make an assumption with the string plot and the string plot for their major PDF function. So that haven't been encoded into the AI.
We discussed this extensively yesterday in Jan's talk, that they're dealing with the inverse problem, right? The global fitting. So therefore, inverse problem, there's no unique answer. Then people do the best in parameterizing it, doing Monte Carlo, whatever neural network and so on. But eventually you want to teach as much physics as it and check as much as you do. But there's no unique answer in the inverse problem as well. So you cannot get a unique answer. That's all we discussed about.
I wanted to say something. So you showed the next slide, and you show this 3GB that it's very striking to me, because I am involved in this kind of calculations, and I know that there is no way one can go to 3GB reliably with the current resources and sourcing separations that you're using. So what is your comment on that? I know that you go up to around 1 Fermi, and we know that boosting the nucleon at 3GB, which is the 14th non-zero momentum, it's very provocative. So I would like to see the data, how they behave on each sourcing separation, and I don't believe that your statistics justifies this momentum.
So when we publish this paper, we will try to release the data on there. People can read it.
So can I ask a related question? This 3GB momentum compared to what is your lattice volume that you use in order to get the 3GB momentum?
5.6 Fermi.
No, I'm talking about lattice points, and I want to know the number of lattice points you had, and the n that you used for the momentum.
I think
so
14.
So the lattice points were 64, and this was the 14th momentum. 64 divided by 16. So it's almost order 1. The 2 pi L times n.
Right.
So have you tried to check what kind of lattice artifacts you have?
We are trying to do that next. So once we have the time, we plan to do that next. Right. And so just to look at the again the iso-vector combination, the difference between the polarized U-plot and polarized down plots. And here we have a similar setup. So again, this is quad and anti-quad. We have delta U distribution mostly larger than delta D, but our error bar wasn't so great. Especially again, the anti-quad is kind of dragging us down as well. And we compare, sort of compare with some of the global PDF hedicity distribution, and they are reasonably well. Obviously, everybody needs some improvement over here. And then this is our latest one. As for the transversity, so the blue one here is our distribution. And then we compare with two distributions, both function collaborations. And we decided to label them differently to sort of not to confuse people. But so this is just purely from the CDS result, which is this gray band that most of the transversity have that kind of errors. And here is the red band over here is the same, about the same fit, but use the latest GT, which is the integral of this quantity to constrain independent lattice calculations and to constrain the fit that's coming to this one. So they are actually quite compatible. And so then again, we look at the the NTC, and we now in contrast what we see in the very small momentums and a much heavier pion mass, and before minimization, we now don't see any flavor symmetry in the transverse polarized anymore. They are mostly consistent with zero. Anyway, so just to say these are all very encouraging, but again, like most of the latest QCD calculation, you need to study systematics. So meaning we had to get a lot of community support to get more time so we can do multiple lattice spacing to check this distribution errors, some of the body effect that people might be worried about, and a lot of stuff we need to check more carefully. Right. So I just want to.
You have a lot of questions, no problem.
So I just want to quickly point out, so this is my grad student, and then Igor when he was in MSU. So together we have been working on trying to take a quick look on can we see anything with a glue-on PDF. And so we use some of the INT-18-3 2 points. They are high statistic. As a starting point, we use overlap. On top of the 2+1 domain, we'll see we have some nucleon, and we just look at the strange point and the light point that corresponding to pion mass. We're still really happy, close to 700 and 300 something, and but we cannot. This kind of calculation is very noisy, so we are trying to calculate a few displacements that we do, and this is we are not SS here is Z times PC, we are not X. And mainly just because you can see after a few displacement with the operator, we get noisy, the data gets really, really noisy very quickly. And the momentum is still small, but here we try to compare with the global PDF with the inverse transformation over here, just sort of get an idea to see how that compares. It's like, it's promising, but there are still a lot of work to be done. But it's looking up. And so I was going to spend roughly 5 minutes to talk about what lattice-QCD can do in terms of the PDF and feature structure functions. So we have a workshop in Oxford last year, and many of the people here were there. So there we have we work on a white papers. So we were looking at what can lattice contribute in, say, the next few years. Among the quantity, we are not calculate directly U and D. We are calculating isobector, the differences between up and down, for example. So there we try to set limits about roughly, what precision. So in this case, we are trying to focus on the large X, where you don't have still don't have a good data constraint over there. So so here's a study try to see what kind of error budget you get from this kind of quantity in this S region, assuming the normal and similar approach. Finally, give us some precise with 4 error bar, multiple lattice spacing, and so on. Assuming if say let's focus on the green line, which is assuming you have total error bar at the end of about 12%, and how much that can contribute in terms of individual anti-quad, anti-up and anti-down. So this is done using the reweighting from an PDF 3.1 version. So there's funny reweighting result at the small s piece, ignore that. But the main message here is you can see a roughly 25-ish% improvements in the individual flavor contributions. So we are not directly calculating individual flavor PDF yet. They are probably another 10 years or longer to do that. But intermediately, looking at these combinations that we can use combined with the global fit to constrain some of, to help out with the region when data is not so precisely constrained, it can actually have some impact. So we are not really replacing any experiment, not anytime soon yet. And so there's also another study looking at how about moments, because we do in the places that we can calculate moment everything. Now we more or less, you know, there's no theoretical issue. They just require people to have sufficient computational power to calculate them. So if you look at the moments, So there, for example, if you want to have impact on the unpolarized case, you need to aim for your final error to be roughly smaller. So again, in the next few years, it's probably possible we can get something, say, about a 5%. And here's the impact on the strange and the dequark. And again, here is the ratio, the gray band here indicate the normalized errors as a function of x. And just if you just focus on, say, 5% final errors, you can drive down to this green band over here, and which can significantly improve on the intermediate region or the leading moments itself. And similarly, as a different reweighting, and you look at the strange, in the polarized case, there the precision required is different. You can actually get away, say, 20% improvements, and you can 20% final error budget, and then as this, you can change the original distribution up to down to the absolute. This is absolute PDF uncertainty up down to by a factor of 2 or less to over here. So it depends on the quantity that required, and the precision required is different for lattice-QCD to make contributions. And there's also, I did this at the last one because often I never have the time to finish my talk if I showed this earlier. So we did this work with NABU, and again we used multiple lattice GT calculation and try to determine lattice average numbers. And then we use that to constrain the CPS analysis. And there we find, again, with the orange bands without lattice GT constraint, and then the individual one is with a lattice constraint. You can change the distribution quite a bit, improve the transversity distribution quite a bit. And just to conclude,
You're fine. No
anyway,
problem.
so it's been very exciting time to study the structure on the lattice. We have been very excitingly trying to study the Birkenhead distribution. We also made some progress on the pion in the meson sector. They turn out to be more complicated than we thought, but we have young people, John Hui, and another student of mine was looking at different kind of meson structures. We started to have some physical parameters result. We expect there will be more improvement result in the future, and I assume we all try to further study the systematic, and this result will become better. And as always, we want to go to larger momentum, and as you go to larger momentum, you also need to go to much smaller lattice spacing. So the problems kind of couple, and it does make the calculation get very expensive very quickly. And then I just want to point out some of the intermediate in the next few years, that what we can lattice calculation can impact the current PDF is likely, things like the iso-vector PDF, even though we are not directly calculating flavor dependent PDF yet, this can still impact from the improved calculation from lattice, and there's also a moment, sorry, on the airplane, moments, and there are other things that we need to think about and we have time to talk about is there are still quite large systematic associated with small X region that we need to think about how to improve them in the future.
Okay, thank you very much. So, some more questions?
We showed the Fourier, but this is a standard Fourier that we showed in the first slide. So you just went through the process, and I think you showed the standard No, for the much earlier, you can go for the transversity, for example. It's just something like that. So here. So you showed earlier the standard Fourier, but if I understand correctly, you use the derivative method. This is discretized, right?
No, it's as discretized as our original Fourier transformation. So that gives you x times f. If you take that.
Yes, I understand that, but how do you interpolate between the points? It's a discretized form of the derivative that you're using.
It's not required. You could do that. It's not required. You have to do that.
I'm just worried about this small x behavior because
the small x.
Yeah.
Well, so it's fall into the part. I didn't have time to show. We do have. It's fall into the part actually small s region that have actually stronger PZ dependence. So there are certain regions that roughly it is this region, probably 0.15-ish. That could be. I won't put my money on it.
But the lattice spacing you have is large. It's almost 1/3. It's 0.09. So I would worry about using this derivative method, and because of the larger discretization effect that can bring in, and you can already see the small x behavior. So we have tested both the standard and these the derivative one, and we don't see that this is better. This could have more systematic uncertainties. For example, you ignore this surface term, and numerically you don't find it to be very small. So it should not be ignored.
No. That's not how we do it. So
this is what your collaborators said at the lattice conference that you were doing. So that's why I'm mentioning it.
Well, there's one you can take a derivative of basically. So you take the whole derivative. So you get x components. How you treat them on the lattice? You can do integration. You can cross check out without that. You can check out.
But you need to have very small lattice spacing.
No, exactly. You can.
I think you do. I'm sorry, but
no, it's basically the same thing. If you take the definition, you take the derivative on both sides. They are equivalent. And if you worry about
surface terms that you ignore, they're not the same. Theoretically, they're the same.
Well, they are not the same because when you do
okay.
We go to that.
Delay. I have a comparison of the two, and then we can discuss in the afternoon session.
So
this is
possible. I knew them. So so there are issues that I didn't want to mention because way too technical. Is you can actually take any known PDF, and you Fourier transform to the coordinate space and transfer it back. You don't always get the same thing. That's what we call it. It's a part of the truncation effect. And because it's a discretized effect. So you start to see, so if you say I take the CT14, usually this green band, you Fourier transform to whatever, to branch out your parameter, you transfer it back, you see there's an artifact that's oscillating, it doesn't recover the original PDF. So that actually happened in our actual latest data. You don't recover them because of the truncation effects. And so the way we propose to look at this, it is a momentum dependence, by the way. When we have a different way you can play around to recover them. Let me see, I have that slide. Yes, so there are, when you try to, this is assuming, we have no large trees in a large Z, assuming you can do very large Z measurement up to 10 or 30, in this case, probably 32. And that you give you very large ZPZ in the Fourier transformations. And if assuming, you don't have to worry about all the other issues, then you can recover most of the quad regions up to certain small x regions. It depends on your momentums. Again, if you have smaller momentum, you have a bigger problems in the small x and anti-quad regions. And even with the large x, assuming, and also very large ZPZ in this case, there will be still some difficulty to try to recover the small x and the anti-quad area. And this is something I mentioned that we need to think about how we can reach a smaller edge region more reliably, because nobody can calculate Z-log day. You have higher twist effect very quickly. So you don't want to keep your displacement too large. I mean, you have to move your momentum even larger. And to get to below that, the momentum we are using probably not enough to get us to this small edge regions. And so without doing polarization or anything else, how can we reliably determine this small edge region in antipolarized? Another challenge that we need to think about. But it is highly sensitive to the parameter we use. So, I mean, you can play around with them. And we do not see a difference. So we use this as a drawing model to see how reliable we can recover. You can play around with your lattice parameter and to see how well you can recover and give us the indices of what's the region of the X you can trust in the approach you use.
Okay, I suggest that some of these details we indeed discuss a little bit more in the afternoon, because there are quite some questions, and that's why we wanted to have a discussion. So first of all, let's thank our random again.